Alright, so today we're looking at the last section in Unit 11, and this is 11-10, and the focus of this section is going to be probability. Okay, now we're going to be looking at several different types of probabilities, and so what we'll do is we'll go through each one, and then we'll kind of sum it all up at the end before we practice some of the problems. Alright, so the first thing that we come to is the probability of an event occurring. Alright, so the probability that something happens, alright, is given by this equation. So the probability of an event occurring is equal to the number of outcomes for that event divided by the number of outcomes in the sample space, or the total number of possible outcomes. Alright, so you can think of probability as a fraction, and it's the fraction of the number of outcomes for the event. Sometimes I like to think about that as the favorable outcomes, or what you want, all right, over the total number of outcomes. So it's favorable outcomes over total outcomes, meaning what you want over the total number of possibilities, or the total number of outcomes possible. All right. So, for example, that's why the probability of flipping a coin and getting tails is 1 over 2. How many tails are there? 1. How many total possible outcomes? 2, heads or tails. Also, the probability of rolling one die and getting a 6 to come up. How many 6s are there? 1. How many total outcomes are there? 6. 1 out of 6. So again, it's what you want. Okay, how many outcomes of what you want over how many possible total outcomes there are, right? And of course, it's important to note that the outcomes are equally likely in the case of the favorable outcomes and in the case of the total outcomes. All outcomes have to be equally likely, all right, for that fraction to be correct. All right, so the next thing that we kind of talk about is this idea of mutually exclusive, okay? And so if you have two events, A and B, from the same sample space, those two events are mutually exclusive when A and B have no outcomes in common. In other words, no common outcomes. All right? And so if you're talking about set notation, this is the intersection of A and B, which would be the empty set, meaning that they have nothing in common. They have no elements in common. All right? So if they don't have any elements in common, then that is known as mutually exclusive. All right, so what we mean by that is, for example, if I say, what's the probability of rolling the dice and either getting a number 3 or getting an odd number? All right, well, those two are not mutually exclusive because 3 is an odd number. Does that make sense? All right, so if I said, well, what's the probability of rolling one die and getting a 3 or getting an even number? Well, those two would be mutually exclusive because they're completely different sets. They have nothing in common. 3 is odd, and then the other even numbers don't include 3. All right? So I'll kind of give you some more examples like that here in just a moment. But let's go ahead and look at how they are found. If A and B are events in the same sample space, then the probability of A or B occurring is given by this. Okay? It would be the probability of A occurring plus the probability of B occurring minus the probability of A intersecting with B. In other words, minus the probability of however many outcomes the two sample spaces have in common, right? And so, again, it's the probability of A plus the probability of B minus the probability of the intersection of A and B. In other words, whichever outcomes are in common to both of these conditions, you got to subtract it off. All right? And of course, if the two events are mutually exclusive, meaning they don't share any outcomes in common, then you just add the probability of each one's together. All right, so we'll get to some problems regarding that here in just a few minutes. All right, so again, if you have two events with some outcomes in common, you've got to subtract off how many common outcomes you have because you don't want to count them twice. All right? But if they're mutually exclusive, you don't have to worry about that because they don't have any outcomes in common. All right? Let's see. Now, the next thing that we're looking at is the probability of independent events. So if A and B are independent events, then the probability that both A and B will occur is given by the probability of A times the probability of B. So again, if you're looking for the probability that more than one thing occurs, then you have to multiply the probability of each individual thing together, provided they're independent. Now, if you have dependent events, in other words, one depends on the other, then the probability that both A and B will occur is given by this. The probability of A times the probability of B after A has already occurred. All right? After A has already occurred. Okay? Now that we've been through everything, let's kind of just sum up each one of these so that we know when to use each formula or what type of probability occurs in different situations. So again, if you just ask for a straight probability, okay, there's nothing to think about as far as mutually exclusive or anything like that. It's just one event. It's favorable over total. How many times does what you want happen over how many possibilities does it have to happen? Very simple to get that probability. Now, when we're talking about the probability of the union of two events, then you're still having one occurrence, or you're just choosing one thing, right? But you want to know what's the probability of getting either one of those things, right? And so again, to distinguish between mutually exclusive and then ones that are not mutually exclusive, you can kind of think about this. Let's say if a deck of cards, for example, if it said, what's the probability of choosing a choosing a heart or choosing a king? Well, there's 4 kings in the deck and there's 13 hearts in the deck, but one of those kings is a heart. So in other words, you don't want to count that twice, so you end up subtracting off the one that they have in common, right? So in other words, if the two things that you are looking to occur, if they have outcomes that are a part of both categories, those are the ones that you have to subtract off. Now, if they're mutually exclusive, that means they don't have any in both categories. Like, for example, if I said, what's the probability of picking an ace or picking a king? Well, there are no aces that are kings and there are no kings that are aces. They're mutually exclusive, so there's nothing to subtract off because you're not counting anything twice. All right? And then, of course, with an independent event, that means the first one has no effect on the second one. Like, for example, the classic example for these would be like choosing marbles. So, like, for example, let's say I have a bag full of marbles and I pick one and then I put it back before I choose the second one. Well, that means the total number of outcomes and everything is the same. Nothing changes. So they're independent events. The first one doesn't have any effect on the probability of the second one. However, if I say, okay, I'm going to pick 2 marbles, but without replacement, I'm not going to put the first one back, okay, then the first choice affects the second choice. For one reason, if I pull one out and leave it out, there's not the same number of marbles in the bag anymore, right? So the total number will be reduced. And if you're trying to pick 2 of the same color, then the number of that color would be reduced. All right, so really dependent events, the classic example is if you're picking something and you leave it out, you don't replace it. All right, so let's just try some examples. Okay, now a lot of probability questions have to do with choosing cards, so it's important to know how many cards there are of each type. So I'll kind of put this up here for those of you who are not familiar with a standard deck of playing cards as to what the numbers are. So a standard deck has 52 cards. The cards are divided into 4 suits, right? So there are 2 black suits, that's the spades and the clubs, and 2 red suits, that's hearts and diamonds, right? So these are the different suits: spades, clubs, hearts, diamonds. All right, so all the cards will have a picture of one of those four things on it. Right? Now in each suit there are 13 cards. So the 13 cards for each suit would be 2, 3, 4, 5, 6, 7, 8, 9, 10. Ace, or Jack, Queen, King, and Ace, right? And so that makes up the 13 cards. So there are 13 of these spades. There are 13 of these clubs, 13 hearts, 13 diamonds, and so on. All right, so that just kind of gives you an idea of how many of each type of card that there are. Okay? Now, let's get into some examples here. Okay, so the first one says one card is selected at random from a standard deck of 52 playing cards. What's the probability that the card is either, okay, a heart or a face card? Now, the first thing that we've got to decide here is what type of probability are we looking at, right? And so, remember, it's basically divided into two categories. Okay, it's picking one thing, right, or picking multiple things, right? So with this, you're just picking one thing, but you may have two different categories of that one thing that's possible, right? So here in these types, you're picking your more than one thing or more than one event is occurring, and you want the probability that both or more of those things would occur, right? So on this one, we're just picking one card, so it's just one thing that's being selected, and we want to know what's the probability that it's either a heart, okay, or a face card. Okay, so this is the probability of the union of two events. I've just got to figure out whether those two things are mutually exclusive, yes or no. Okay, so the question is that I've got to figure out is, are there any face cards that are hearts, or are hearts one set and then face cards a totally different set? That's what we've got to figure out. Okay, well, remember, in the hearts, you've got 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and Ace, right? So there are 3 face cards that are also hearts. So since that's the case, since they overlap, right, then these are not mutually exclusive, and then we'll have to use this first formula. All right, so the probability of the union of those two things. Okay, so let's think about it. Okay, first of all, it's going to be the probability of the first thing. All right, so the first thing is it being a heart. Well, how many hearts are there in the deck? Okay, and there are 13 hearts of each suit, or 13 cards of each suit, so there would be 13 hearts in the deck. Out of how many total cards? Well, there'd be 52 total cards. Okay, so that's the probability of the first event occurring. Now, I need to add to that the probability of the second event occurring. All right, probability of the second event is that I'm getting a face card, right? What's the probability of me getting a face card? Well, there are 3 face cards in each suit: Jack, Queen, and King. Ace doesn't have a face on it, so it's not a face card. But there are 3 in each suit. There's 4 suits. 3 times 4 makes 12. There are 12 face cards in the deck. That's 12 over 52. Now, remember, these two events are not mutually exclusive because they do have cards that are a part of both categories, right? So I need to subtract off whichever cards are a part of both categories. All right, so how many cards are hearts and face cards? Well, remember, each suit has 3 face cards, so I'm going to subtract off the 3 out of 52. And that is going to be this portion of the formula right here. Subtracting off the union of these two events, or subtracting off the probability of the cards that are in both categories. All right. So let's see what we got here. So we've got 13. Go ahead and subtract that 3 off and make that 10 plus 12 is 22. So the probability is 22 out of 52. Now remember, in probability you always want to reduce your fraction. So that's 11 over 26. So 11 over 26, a little bit less than half. You can express your probability as a fraction, but you could also express it as a decimal and turn the decimal into a percent. So if you want to divide this out and then turn that into a percent, that also kind of gives you an idea of how likely it would be. All right? Okay, now the next thing we want to look at. Okay, so one card is selected. So once again, since one card is selected, that's the probability of a union, right? And it says one card is selected at random from a standard deck. What's the probability that the card is either a heart or a club? All right, so what we need to decide is choosing a heart or a club, are those two mutually exclusive, or is there some overlap? Well, remember, hearts, a heart is one suit, and there's 13 of those cards, and a club is a completely different suit. So the question is, are there any clubs that are hearts? And the answer to that question is no, because they are two completely separate suits. So what that means is that these two events are mutually exclusive because there are no cards that are a heart and a club at the same time, right? So in the last one, there were cards that were hearts and face cards at the same time, okay? But there are no cards that are hearts and clubs at the same time. So since that's the case, there's no card in both categories. That's what it means to be mutually exclusive. So hopefully that gives you a better understanding. Okay, so all I have to do is, since they're mutually exclusive, I just have to add the probability of each one together. So what's the probability of getting a heart? Well, how many hearts are in the deck? There are 13. 13 over 52 plus how many clubs in the deck? 13 over 52. So I have to add those two probabilities together to get 26 over 52. And once again, we need to reduce this fraction. And you can probably find a fraction reducer online pretty quickly. But the fraction here actually reduces to 1/2. So you got 1/2 is the probability, or 50% chance of choosing a card that's either a heart or a club. Okay? Alright, so now we're getting into some examples of the probability of independent and dependent events. Now, remember, these first two are just the probability of one thing occurring, right? Just one choice or one pick. Alright, it's really the probability of just one thing. Here we'll have the probability of multiple things occurring. So that's kind of the difference between the two. Alright, so the probability of independent events. Okay? So let's read it. A random number generator on a computer selects three integers from 1 to 20. What is the probability that all three numbers are less than or equal to 5? Okay, so kind of the major difference between the two is here you just have one thing that's being selected. Here we've got three things that are being selected. Okay, so here you've got two different categories of one thing that are being selected. But here you've got three completely different things that are being selected. So that's kind of the difference. So here if it's just one thing, you have to add the probabilities of each thing. Okay, but if you've got three different things that are happening, or the probability of three different events that are occurring, then you have to multiply the probability of each one together. And that would be the probability that all of them occur. Alright, so let's take a look at each one of these. So what is the probability that the first number is less than or equal to 5? Well, how many numbers are less than and equal to 5 from 1 to 20? Well, it would be 5. And again, out of how many numbers does the generator have to choose from? 20. So the probability that the first number is less than or equal to 5 is 5 out of 20. Okay? Now, the next thing that we want to try to figure out is it already told us that these are independent events, but let's just verify that. Okay? So, does the first pick affect the second pick, the probability of the second pick in any way? The answer is no, because the generator is still picking a number from 1 to 20, so the numbers don't change. So what's the probability that it's less than or equal to 5? Well, it's still 5 out of 20. And what about for the third number? It's still 5 out of 20. And what does the formula say I need to do with each one of those events? I need to multiply them together. So I'm going to multiply all three of these events together to give me 5 times 5 is 125. 20 times 20 times 20 is 8,000. And using a fraction reducer that you can find online, you can see that that probability is 1 out of 64. So you have a 1 out of 64 chance that all three numbers picked are less than or equal to 5. Alright? So the probability that if you just pick one number, it'd be 5 out of 20, or 1/4. But if you do it 3 times, the probability that all three would be less than or equal to 5 is 1 out of 64. So you can kind of see the difference there. Alright, what about the last one then? This is the probability of dependent events. So the first event is going to have an effect on the numbers for the second event, and so on. Alright, so 2 marbles are picked without replacement, and that's the key. That's what makes these dependent events, is because you take a marble out and you do not replace it. Okay, from a bag containing 5 red, 3 green, and 2 blue marbles. Find the probability that the first marble is green, okay, and that the second one is red. So I want to find the probability that the first marble is green and that the second one is red. Okay, so let's find the probability that the first marble is green. So how many greens in the bag? 3. Out of how many total to choose from? 5 plus 3 plus 2 makes 10. Okay? I'm going to multiply that now by the probability that the second one is red. Okay, now remember, I'm picking a green marble on the first pick and I'm leaving it out without replacement. I do not put it back in the box. Alright? And so if I do not put it back in the box or in the bag, then what that means is that's going to affect the numbers on the second one. Now I need the second one to be red. How many reds are still in the bag? 5, because I did not pick a red one on the first try. Now how many are still in the bag to choose from total? Not 10 anymore, because I pulled one out and left it out. It's down to 9. Alright? So that's why these are dependent events, because the first one affects the numbers for the second one. Okay? So remember, with dependent events, it's the probability of the first one times the probability of the second one after the first one has occurred. Well, after I pull one green marble out, there's only 9 left to choose from. Okay? So that's what makes them dependent events. Okay? Now let me go ahead and say this too. Alright? If I were trying to pick 2 of the same color, then not only the bottom number would drop, but the top number would have to drop as well, because remember, I'm pulling it out and leaving it out. So if it was the same color, in other words, if it was the first one is green and the second one is green, well, it wouldn't be 3 green anymore, it'd be down to 2. Alright, so just keep that in mind, because you're picking one out and you're leaving it out. Alright, now multiplication together, that would be 3 times 5 to get 15. And on the bottom, that would be 9 times 10 to get 90. Once again, we got to make sure that we reduce our fraction. If you don't reduce it, of course, it's not going to be correct. So we must reduce it down to lowest terms and make that 1 over 6. So you have a 1 out of 6 chance of picking a green marble on the first pick and a red marble on the second pick without replacement. All right? That's it.